Hello guys, welcome to JJK Masterclass. Guys, since we are meeting after a very long time, here I am having a very special video for you on retrosynthetic analysis, where we'll be discussing about problems and its solutions on disconnection methods and its synthesis. Since all of you are preparing for M.Sc examination, this particular topic is very important for M.Sc students, and I hope this video is going to help you to solve many more problems on it. So let's start. Since we'll be discussing problems here, so our very first problem is sketch retrosynthetic analysis and give a synthesis for the following molecule. So a molecule will be given to you and they will ask you the retrosynthetic analysis, means you have to find out the starting material to design this target molecule. So how to do that, we'll see. So first, to find out the starting material for this, we will do the disconnection on this molecule. So you are having this molecule here. So whenever you have a molecule and you see it is a bifunctional molecule, just try to find out whether the position of the two functional groups is it 1,3 or 1,5. So if we see with respect to this carbonyl, let's say, so then carbonyl is having 1, 2, 3, 4. The position is 1, 4. So here we cannot apply that 1, 3 or 1, 5 bifunctional property and disconnection method. So the next is, if you look at this molecule, you can see here OH is on the branch side, so we normally don't prefer to disconnect this type of functional group which is on the terminal side. So if we focus on the carbonyl group, with respect to that you have learned 1,1 disconnection and 1,2 disconnection. So we'll see the position here with respect to carbonyl 1 and 2. So if let's say you disconnect this 2,3 bond here, so we call it 1,2 CC disconnection. So since you are disconnecting a carbon-carbon bond here, one carbon will be getting a positive charge, the other carbon will getting a negative charge. Now how to decide which carbon will get a negative and which carbon will get a positive charge? So we'll see, let's say we have disconnected it and you have given a negative charge to this carbon 2 and carbon 3 is having a positive charge. Now why I have given this? Because you can see the carbon 2 is having the acidic proton, and when you do the synthesis in the presence of a base, the proton will abstract this carbon 2 proton easily, because this proton, when you abstract, generate a carbanion and which is getting resonance with the carbonyl group, so getting a stabilization, and we can say that this carbon 2 proton is acidic proton. So therefore with respect to that, I have given here the second carbon as a negative charge, because you can show the resonance here, it is stabilized, and the other side you can see it is having a positive charge. So now these are called synthons. In retrosynthetic analysis, you can find these terms: target molecule, synthons. So now we have to decide what are the synthetic equivalent for the synthons, because synthons is not which you are having commercially available. So you have to find out the synthetic equivalent which will act as a starting material. And we know already that minus species are going to stabilize by positive species. So here I have written H plus here. There are other possibilities also. You can stabilize it with any positive species if you want. And here positive species is usually going to stabilize by negative species. So here we are having, since OH on the same carbon, you can see the lone pair of oxygen will form a bond here and will give you the best synthetic equivalent. You have here acetone if you stabilize it with positive charge, and the other side you are forming a epoxide, and the two are easily available starting materials, and you can easily design the epoxide also. So the two are the starting materials for the synthesis of your target molecule. So now we'll be seeing these two are called the synthetic equivalents, which are the starting material for your synthesis. So now we'll see the synthesis of this molecule using these starting materials, and you can notice here We are doing the reaction in the presence of base, and base will abstract the acidic proton. So here you will be having acetone in the presence of base first, and then generation of a carbon ion. Here we know the carbon bearing a negative charge or oxygen bearing a negative charge. We know oxygen can better accommodate a negative charge, so we'll show the negative charge on the oxygen here, and the reaction will proceed with the resonating structure through the carbonyl bond formation, and the carbon will generate a negative charge. So now here you have this carbon ion which is acting as a nucleophile will attack. Two possibilities are there for this epoxide ring opening. Either it will attack the arrow which I have shown, or you have the other side where you have substituted methyl group. So if you notice one side, if you see it is substituted methyl will have a, this carbon is having a steric crowding. So here the preference will be less to attack for this nucleophile. Therefore, we will show the attack of this nucleophile where you have less steric crowding, and so the ring opening will take place like this, and you will show the formation of a carbon ion here. So this is like you're getting the structure, and after protonation you will get your target molecule. So this is how you are designing this particular target molecule by using with the help of disconnection. We are finding the starting material, and then this is your normal chemical reactions which you are doing with the help of the knowledge of the reagents and mechanism. You can design the synthesis. Now next is, you can notice here the problem. Outline the retrosynthetic route involving Wittig and Diels-Alder reaction for the following molecule. So a molecule is given to you, and here they have asked you to find out through Wittig and Diels-Alder reaction. So we'll see how we can do it. So first we'll see through disconnection, as they want us to find out. So if you notice this molecule is having a 6-membered ring having a double bond, and you have a exo double bond here. So if you have a knowledge of Diels-Alder reaction when it forms a 6-membered ring with one double bond. So basically, when you do the retrosynthesis of it, you will be getting a diene and a dienophile. And we know in Diels-Alder, the diene act as this electron donor, while your dienophile will act as an electron acceptor. So here you should have an electron withdrawing group. So here we will take the help of Wittig reaction, which converts a double bond to exo double bond to a carbonyl group. So we'll do the FGI here, which is functional group interconversion. Wittig reagent which converts the exo double bond to carbonyl, and we'll get this molecule. So once you get this molecule, this is a perfect structure or product of the Diels-Alder. We'll do the retrosynthesis of it, and we'll find out the starting material, which is your diene and dienophile here. So now we'll see the synthesis with the help of these two, and we know Diels-Alder reaction is the 4+2 cycloaddition reaction, and you can show the same structure as we have drawn here in the disconnection. And now you have a carbonyl here, and in the target molecule you have a double bond. So we know we can apply the Wittig reagent here. So PPSV double bond CH2, because we need only one carbon here. So it is going to form a halide followed by a betaine intermediate, which will give you the exo double bond. So I hope you are familiar of the Wittig reaction and its mechanism. If you not, you can refer the textbook for this, and you can find out how it converts. Since here we don't require the mechanism, you should know that the carbonyl group in the presence of Wittig reagent, it converts into exo double bond. So this is how you can design this particular target molecule with the help of Wittig and Diels-Alder reaction. Next problem, you can notice here they are asking you, using two group disconnection approach, identify suitable synthons which may be used for the synthesis of this molecule. So they have given you a clue here. So we'll find out the disconnection approach, as they are saying 2 group disconnection approach. So we have a 2 functional group here. We'll find out the position. So if you count from carbonyl 1, 2, 3, the position is 1, 3 to each other. And if you are familiar that when you apply 1, 3 disconnection, we usually break 2, 3 bond. So if you break 2,3 bond here, you will get again, this is CC bond disconnection. So one carbon will get a positive, the other will get a negative, and we know which carbon is going to have a negative based on the stability of this carbon ion, and you are having a positive on the other side. These are called synthons, and which you can stabilize by the respective opposite charges. So we are writing the synthetic equivalent here. As you can notice here, so you have the carbon which is bearing a positive charge, and the same carbon is having OH group. So when you have such kind of synthons, you can write down the carbonyl group here, like this proton will give its electron to this carbon, and so you are forming a carbonyl bond here. Since you don't have any other substituent here, you can write hydrogen. So this aldehyde is the synthetic equivalent for the designing of this molecule, target molecule. Now the other side, in the previous case we have written with the hydrogen here, right? Negative species will stabilize by positive hydrogen. But if you write here hydrogen, then you will get a acetone here, and acetone and aldehyde, if you treat as a starting material for the synthesis, the two are the cross condensation reaction. Okay, so the synthesis will go through the cross condensation because you have two different carbonyl groups. So when you have a cross condensation, you must have read already in retrosynthesis that multiple products chances are there, chemoselectivity issue will be there to design your target molecule. So in that case, we always design the specific equivalent for your target molecule. So here we'll be writing the specific equivalent. Here we have written the organozinc as a opponent here to stabilize this negative species. So it is forming a organozinc here, which is, like we know, the metal is being electropositive, will get a positive charge, and here your carbon is a negative charge. If you notice why we have written this particular synthetic equivalent, you can notice here this is beta hydroxycarbonyl compound, and we know, if you're familiar of Retrosynthetic reaction, it gives you beta hydroxycarbonyl compound as a product. So this is the best equivalent we can suggest for this reaction. There are other possible synthetic equivalent also which you can write. So but we always select the most reliable route which gives you the target molecule only. So we have selected here the organozinc here, which is basically, if you see Retrosynthetic reaction is having the alpha halo ester here. So R may be your OET, you can say here. So it is alpha halo ester you can design, where in the presence of zinc, insertion will take place between the carbon and Br bond. So you are getting this reagent, and now since you are having this reagent ready, you can have this nucleophile to attack on the carbon which is acting as an electrophile here, and you will get after protonation this beta hydroxycarbonyl compound as a product, and which is our target molecule, if you can notice. So this is how you can design your beta hydroxycarbonyl compounds using Retrosynthetic reaction. Next, a problem you can notice here. Again, a molecule is given and they are asking you retrosynthesis of it. So we always go by disconnection method first. And if you notice this molecule, we have OH group, and you have on the same carbon two same groups like phenyl groups. Since you are familiar of, I assume that you have studied all the synthetic, retrosynthetic rules, disconnection approaches. So once you have learned revise all the topics related to it, then you will be able to solve such kind of problems. So here we'll see the rule says that when your carbon, which is having the OH group, having two same groups, we use the double disconnection approach. So here we'll be doing the 1,1 cc disconnection. So both pH we are going to disconnect here, and we'll be getting here synthons. Carbon which is having OH will get a positive charge, and the phenyl will get a negative charge here. So these are the synthons, and we'll be writing the synthetic equivalent because The synthetic equivalents are the starting material to design your target molecule. And just now we have seen, if your carbon here, you can write down this carbon is having OH group. So just you can rectify this. Carbon is having OH group here. So you will be writing here this. Okay, so you will be getting positive charge with OH group. So positive charge OH group, we know we write this. So either you can write down ester here, or you can write down, if your positive charge, the species is having OH group, aldehyde. Okay, so you can write down aldehyde here. In that case, either I have written ester. Since the small changes, because by mistake I have written here a carbonyl group, so accordingly I have designed ester here. So but if you write down a carbon positive with OH, we can design here aldehyde also. And we know the Grignard reagent, you can write down pH minus here, so which is getting a Grignard reagent formation here. So magnesium being electropositive metal, you will get a negative on pH. So the nucleophilic attack of Grignard reagent on the aldehyde will give you the target molecule. Here I have used OET. Since I have shown here carbonyl, so carbonyl is having a positive charge, so you can stabilize with negative species. So small changes, because of with respect to this synthon, I have designed here ester. You can design here with COH, the positive charge aldehyde group here. Okay, so using that you can synthesize. This is nothing but the nucleophilic attack of the Grignard reagent on the carbonyl carbon will give you the target molecule. So one side I have shown here with the loss of OET, you are getting this molecule. Again you have a carbonyl molecule here. So you can show the second time attack of this pH molecule after hydrolysis will give you the target molecule. So this is how you can design your target molecule when you have method applying 2,1,1-cc disconnection method. Next molecule, you can see a aromatic molecule, which is here you have three side it is substituted. So we'll be seeing how to find out the starting material for this. So here we'll be doing functional group interconversion here, and disconnection to get the starting material. Usually we see in such kind of molecules we get toluene as a starting material. So how to do that, we'll be saying. First we'll be doing FGI, where we'll be doing the substitution. And having substitution, we can convert this OH group into NH2. And why we are doing that, we know that NH2 later we can do reduction, means you can do oxidation in synthesis and convert it into nitro group, nitration. Okay, so we'll be seeing here disconnection approach. So now like you have converted NH2. Next we are disconnecting this Br group from here. So you are getting here amine and Me group only, which we will do FGI again. Using reduction here we can write down nitro group. As you know that we write down the this is a retrosynthetic arrow. On below of it we write down the reduction, because when you do the synthesis from NO2 you are going to reduce and get the NH2 here. So this term which we are writing is with respect to the synthesis. And remember, this disconnection approach is a mental approach. Actually it is not happening mentally, we are doing it to get your starting material. So once you convert it into NO2, we can do the CN disconnection and you can get the smallest unit, toluene, as a starting material, which is easily available. So since you got the starting material, we can synthesize. The steps will go in just reverse direction like we are synthesizing. So first we will be doing the nitration here, and Me being orthopara directing, it will give you para substituted NO2 here as a major product, and where we will be using the tin concentrated HCl, which reduces the NO2 group into NH2, and you get your next the parent compound for your next target molecule. So after that we know NH2 is being active. We will be protecting it and reducing its activity with acetylation. So you are protecting here NHAC, Then we will be doing bromination here, and bromination will take place at the ortho position of this group, because you have here two groups which are para directing, but the one which is having the most powerful electron, this donating group, or you can say ortho para directing group, it will refer it. So with respect to NHAC, ortho position is this one, para is already occupied, so the bromination will take place at ortho position of this, which is you have studied already how to do the substitution. And then later you can notice the starting material is having OH, so you'll be converting this by using NaNO2H2SO4, and hydrolysis of this compound will give you your target molecule. So this is how you can use the disconnection approach to get the target starting material, and then go reverse in the same direction to get your target molecule. Next, we'll be seeing a question where the conversion is given to you. So basically, this is a synthesis. They are asking you, the starting material is given and the target materials are given to you. You have to synthesize these molecules. So we'll be seeing the synthesis. First molecule is there where you have aldehyde, and you have to design this product. So you can notice the product is alpha beta unsaturated carbonyl, and if you are familiar of the condensation reaction, then you can notice this is the self condensation reaction. You can conduct it either in the presence of base or acid. So here we are doing in the presence of base, which will abstract the acidic proton and getting stabilization. Here you can notice oxygen can accommodate a better negative charge, so we are writing here negative instead of writing a carbon having a negative charge. And so you can notice the reaction, the nucleophilic attack of this carbon on the carbonyl carbon of the other molecule of aldehyde, and you'll be getting after hydrolysis the product which is the beta hydroxycarbonyl compound. And since beta hydroxycarbonyl compound, it has a tendency to release a water if you heat this molecule in the presence of acid, so you get the alpha beta unsaturated carbonyl compound here. And if you notice, this is nothing but a very famous named reaction called aldol condensation reaction, which is a self condensation reaction. So this is how you can synthesize the first molecule, where you are converting a carbonyl group to the alpha beta unsaturated carbonyl group. So here it is aldehyde. You can have here carbonyl ketone also. The next molecule is given to you is cyclohexanone, and we have to design a molecule having exo CHO group. So first of all, we know when you have to generate a carbon which is exo to this, we use the Wittig reagent to convert it. So basically, first we'll be converting this carbonyl group to the exo double bond group. So once you convert it with the help of Wittig reagent, next is we'll be using here borane, which is a reducing agent, and the addition will take place of this reagent on the double bond, and then you'll be getting here this structure. So borane being a bulky group, it will act on the terminal carbon, and so after hydrolysis in the presence of peroxide, it will give you the alcohol. So once you get the alcohol, then it's very easy to get the aldehyde after oxidation reaction on alcohol. In the presence of pyridinium chlorochromate, you can do it, and you will get your desired target molecule. So this is how you can solve this problem, and all the problems which we are discussing here belongs to your question paper only, the previous years of question paper. So I think these are going to help you to solve many more problems. The next problem is there given you that mention the use of carbonyl condensation. You have to synthesize this following molecule. So you can notice here two carbonyl groups are there in the product. So in your target molecule, so it is a condensation reaction. Now how to find out this starting material to design it? So for that we'll take the help of disconnection method first. And if you notice, you have a two functional group here. So when you have two functional group, we find out the position of these two. So if you notice, I have given number 1, 2 and 3. So the position of the two functional groups are 1,3 to each other, and so we'll be applying 1,3 disconnection. And this is a retrosynthetic arrow, as I told you, and it's a mental approach. Disconnection method is a mental approach. So here the rule says when you have 1,3 disconnection, we usually break the bond, the carbon-carbon bond between 2 and 3 carbon. So if you do so, we'll get again one carbon as a positive, other as a negative. So we know that we'll be writing the carbon one negative where you have a resonance here which can stabilize. So basically this proton will be acidic. So it is going to be abstracted easily in the presence of base when you're going to synthesize. So we'll write here minus, and the other carbon will get a positive charge. Here you have carbonyl already, so we'll be stabilizing with the negative species. So we'll find out which are the suitable starting material for this or synthetic equivalent. As you notice, the two are different carbonyl groups, so you will be having the cross condensation reaction. And if you notice that you might have learned about cross condensation, when you have cross condensation, chemoselectivity issue comes. So we select the suitable synthetic equivalent where you'll be having one carbonyl group which will act as a enol, the other will act as a electrophile only. So we will be finding it. So here you can see I have written here cyclopentanone, and other I have stabilized this positive charge with a negative species. So negative we have written here OET species, oxygen being a negative charge. So we have written the synthetic equivalent this, where you can notice here you don't have any enolizable proton. So basically this particular carbonyl group will act as an electrophile. So only one will act as an enol, means proton will be abstracted, the other will act as only electrophile. So one side reaction will be there. In that way we are reducing this and resolving the chemoselectivity issue. So these are the starting material for our target molecule. In the presence of base, we know it abstracts the acidic proton and it forms enolate, and later you can show the mechanism. The carbon ion which is coming here will attack on the electrophilic carbon, followed by the loss of OET. You will get your target molecule in very less time and small single steps. So this is your target molecule. You can write and design many other syntheses to find your target molecule, but this approach gives you the result with a more probability and more reliable route. So this will be the last problem for in this video. We'll be discussing some other problems from your question papers in the upcoming video. So we'll discuss here two molecules are given. One is a alpha beta unsaturated. So we'll start first to find out the starting material to design it. We'll take the help of disconnection. And whenever you have a alpha beta unsaturated molecule as a target molecule, we know that we have learned we do the alpha beta disconnection. And when you do that, you put on the beta carbon a carbonyl group. So we'll be doing alpha beta, and the beta carbon will get a carbonyl group, and the other you have here you will get a negative charge, and that negative charge will going to write down here the suitable synthetic equivalent for that, because here your carbonyl is acting as an electrophile. So the other should act as a here you have to stabilize with the positive species, should form a enol content here. So if carbonyl is acting as an electrophile, the other should act as a enol. So we'll be stabilizing it. There are again many methods. So we'll be using here Wittig reagent, where again phosphorus being electropositive, it will get a positive charge, carbon will get a negative charge. You may also stabilize it with the positive species like COOET, and then you can find out the enol content there, and you can pursue for the synthesis. So here we'll be writing the phosphorus reagent, which is Wittig reagent, and we'll use that to synthesize your target molecule. So we know here the phosphorus halide is there, which forms the betaine intermediate, if you're familiar with Wittig reagent, with the carbonyl compound, and then with the loss of this reagent it will give you the alpha beta unsaturated carbonyl compound. You can notice this mechanism, and in very less time you are getting the target molecule, that is alpha beta unsaturated carbonyl molecule. The other molecule which will be synthesizing, you can see again will take the help of disconnection method. So now again two functional groups are there, so we'll be find out the position of these two functional group. So if you do numbering 1 2 3 4 5, we 1,5 disconnection, we do the cleavage on between 3 and 4 carbon. So you could have done the numbering of with respect to this carbonyl ring, carbonyl 1 2 3, but then we won't get the correct fragmentation, because normally we prefer to fragment on the branch side which is connected to the ring. So therefore I have done the numbering with respect to the ester carbonyl here, so that we get a correct fragmentation from the branch here. So 1,5 disconnection, again it is CC disconnection. One will get a negative, the other carbon will get a positive charge. With respect to the same concept here, this is getting stabilization. So we'll get a negative charge here. You can stabilize with positive species, that may be hydrogen. You will get cyclohexanone. The other is having positive charge here, and whenever you do 1,5 disconnection, definitely one of the synthetic equivalent you will get alpha beta unsaturated. So as you can notice here, this carbon I have mentioned is acidic, and when you do synthesis, so it can easily eliminate a proton here, and you can find out a double bond formation. So this is like you make a note whenever you have done the 1,5 disconnection, one of the synthetic equivalent you can straightforward write as a alpha beta unsaturated. So now these are the two starting material which we got, and we'll use the two for the synthesis. And if you could notice that the two reactions again will be converting into this carbonyl first into like with the help of secondary amine into N-amine content, because now again we have to design the specific equivalents. So we have converted this carbonyl, the reaction between carbonyl and secondary amine, to N-amines here, which gives you the which resolve your chemoselectivity issue. Okay, so therefore we have written this synthetic equivalent, and N-amines will react to this alpha beta unsaturated, which is the Michael addition reaction, which is very familiar reaction and reliable reaction. You will get here amines, which on hydrolysis will give you the, so here resonance you can show as we have generated enol. So I have written carbonyl after this. After hydrolysis, we will get your target molecule, which is you can see you have 1,5 dicarbonyl target molecule. And this is how, with the help of disconnection method, you can find out the suitable starting material to synthesize your target molecule. So I hope all these problems which we have discussed today will help you a lot to solve your questions in your upcoming exam. Happy learning.